Popova. Maia did her PhD with Stacey Lowry Bretz at Miami University, Ohio. And she's currently a postdoc with Marilyn Staines at University of Nebraska-Lincoln. Like Kinsey, she also has a very significant publication record. For somebody at her stage, it's very impressive, around the area of looking at student learning in organic chemistry, and she's going to be sharing some of that work with us now. I see her microphone is turned on and ready to go, so Maia, thank you very much. I will pass over to you.
Thank you so much for this nice introduction. I am really excited for this opportunity to present here today. And as Michael said, we will now shift our focus on students learning in organic chemistry classrooms. And the topic of my talk today is looking at how students make connections between reactions and reaction coordinate diagrams. So if we think about the 10 anchoring concepts in organic chemistry that were identified by the ACS Exam Institute, energetics were identified as one of those key concepts that students have to learn as they take chemistry. However, there's a big body of literature that shows that actually students experience a lot of difficulties when they have to make sense of how the energy is changing as reaction progresses, as bonds break and form. And when we teach about reactions, reaction coordinate diagrams can serve as this nice tool to help students visualize the energetic changes that occur in a reaction. For this reason, we decided to dive in a little bit deeper and see how students make sense of reaction coordinate diagrams and how are they able to make connections between reactions and reaction coordinate diagrams. And so the two research questions that I'm addressing here in this talk is really looking at students' ability to make between reactions and reaction coordinate diagrams, both from looking at what they say and then at what they draw. And I will share with you today some of our findings, but if you are seeking for more details, I will encourage you to check those 3 publications on this slide to get more insight and detail on our findings here. So who was our sample? For this study, we interviewed 36 students that were enrolled in Organic Chemistry 2, and we purposefully selected students that showed different performance in Organic Chemistry 1. So we have 14 students that earned A in Organic Chemistry 1, 14 students who earned B, and 8 students who earned C. And in our sample, we had 28 non-majors. As you can see, majority of our participants are biology majors, we have chemical engineering majors, and so forth. And an IRB application was submitted and approved prior to starting collecting data. And we assigned pseudonyms to each student in our sample to protect students' identities. So how did we collect data? As I said, we conducted semi-structured think aloud interviews, and we made sure to collect what students say, what students draw, and also their gestures. So the video camera was focused on capturing students' gestures, their hands moving, and their worksheets that they were working on. And so what did the interview prompt look like? What did we ask students to do during interviews? So each interview was assigned 2 reactions, 1 substitution and 1 elimination. On this slide, you are seeing a substitution reaction from our study. And students were asked to match each of the assigned reactions to a reaction coordinate diagram. And I would like to engage the audience here a little bit, and we'll give you a second to think about which reaction coordinate diagram do you think corresponds to this substitution reaction on the slide. And you can even feel free to type your responses in a chat if you're feeling comfortable with that. You can either just take a mental note for yourself or write down your response. So with that, I will to breaking it down for you, giving you the answer. So as we can see, this is not a one-step reaction, so definitely reaction coordinate diagram would not correspond to this reaction. And okay, I see one response here in the chat. Yes, B is the correct answer because we have 2 intermediates forming in this mechanism, and one intermediate, the carbocation intermediate, will be higher in energy than the hexanium intermediate because we're lacking an octet there. So yes, B is the correct answer. So that's what students were supposed to do. They were supposed to match their two reactions assigned to a reaction coordinate diagram. We analyzed the data by inductively coding the interview data, and we performed constant comparative analysis to make sense of what students were saying, and then we also analyzed students' drawings of reaction coordinate diagrams to get an additional insight about their understanding and ability to make connections between the reactions and the reaction coordinate diagrams. The trustworthiness of our analysis was ensured by researchers' weekly meetings where the codes were discussed and revised, and confirmability and credibility of our analysis was ensured by peer scrutiny with other researchers that were uninvolved with the project within the institution where the study was performed. And with that, let's get to results. As I will remind you again, students were asked to make connections between two reactions and reaction coordinate diagrams, and we had 36 students in our sample. So out of the 36 students in our sample, 6 matched both their reactions correctly, so that's great. However, 30 students made mistakes. We have 16 students who matched one of their reactions correctly, and we have 14 students who made mistakes with both of their reactions. We performed thematic analysis, and we were able to identify 3 themes that explain the challenges that students had with this task. So challenge number 1 is students were not interpreting correctly the surface features of reaction coordinate diagrams. Challenge 2 is students making mistakes when interpreting the reaction mechanisms themselves. And challenge number 3, students not being able to identify the relative energies of reaction species. And I will draw your attention that some students showed 2 challenges at the same time. So, for example, we can see that there are 6 students at the intercept of theme 1 and theme 3. However, good news, I guess, is that we didn't find any students that showed all 3 of these challenges. So for the sake of the time today with this talk, I will focus more deeply on theme 1, and we will explore a little bit more about what are those struggles that students had with interpreting the surface features of reaction coordinate diagrams. So we can look at this as, so we can look at an example that demonstrates this challenge. So I have the same that I showed you a few slides ago, and we have the correct answer at the top. So let's look at what a student in our study did here. So as you can see, we have a response from a non-major student, Vera, who she actually drew her own reaction coordinate diagram. She told us that none of the options that we provided her were correct. So here's what she's saying. I'm not sure that this reaction has 3 peaks. I guess I will just assign the 2 intermediates depending on energy. I think the second intermediate is going to be higher in energy. So as we can see, Vera thinks that the peaks in reaction coordinate diagrams represent intermediates. So for this reason, she has the 2 intermediates above the peaks. Then I asked her, what does this, what does the value then represent when it comes to this reaction? So then she drew this transition state-like looking structure where we have this dotted line representing bond formation. So obviously we can see that this student failed to make the proper connection because she didn't know how to properly interpret the reaction coordinate diagram. So now let's look at how do students make sense of these reaction coordinate diagrams. So we decided to dive in a little bit deeper here and try to understand how students interpret the starting point, ending point, the peak, the valley, height of the peak, and the width of the peak. And students in our study were shown 3 reaction coordinate diagrams and were asked to explain what meanings they attribute to each of these surface features. And in order to analyze students' responses, we use this deductive coding rubric designed by Abraham and colleagues, where we were categorizing students' responses by their level of understanding. So the responses were coded as sound understanding when students provided a response that was correct and complete. So here's an example from student Inga, who was interpreting starting point, and she says that the starting point shows the original energy of the starting reactants. So as we can see, Inga correctly tells us starting point represents reactants, but she's also mentioning the energy, specifically the energy of the starting reactants, meaning that she pays attention both to the x-axis and y-axis. Responses were quoted as partial understanding when students provided correct responses, but their responses were incomplete. So here we have an example quote from Maxime, who was asked to interpret ending point of a reaction coordinate diagram. And he says it shows it's when the reaction has reached completion, and that is when you have your products. So as we can see, Maxime correctly identifies that products are encoded at the ending point of reaction coordinate diagrams. However, as he was talking about the different surface features of reaction coordinate diagrams, he never mentioned energy, so he was ignoring the y-axis. So this response being correct but incomplete. Responses were quoted as partial understanding with specific misconception when part of the student's response was correct and the other part contained a misconception, or students were did not use proper terminology. So here we have an example quote from Alisa, and Alisa was interpreting peaks and valleys. So here's what she says. Peaks represent the two intermediates because reaction goes in two steps. So as we can see, she understands that peaks represent steps of reactions, so that's correct information. However, she says that the peaks represent two intermediates, which is incorrect. I followed up and I asked her, what does an intermediate mean? And she says intermediate is the middle phase. Not all of the bonds are completely broken and new ones are formed. So the definition that she provides kind of sounds like a definition for transition state. And then we go into asking her about the meaning of the valley, which she says the valley represents the product of the first step. So at first glance, we might think Alisa doesn't know what she's talking about really, but when we look a little bit closer into her response, we see that she actually conceptually understands which chemical species are encoded at the peak and at the valley. She's just mixing her terminology. She's calling what's encoded, she's calling transition states intermediates, and she's calling intermediates products of a reaction step. Responses were quoted as specific conception when the entire response contained incorrect information. Here we have a quote from Yelena, who has to interpret the meaning of peak width, and Yelena says that peak width shows how long it takes for that step to happen. So Yelena thinks that peak width represents time. And finally, we had a category of no understanding. This is when students attempt to provide a response but fail because they either forgot or they just don't know. So here we have an example quote from Alina, who says, yeah, valleys, they do have a meaning. You compare, it's always the bottom of the peak. Okay, there is K, no, not it's K. I definitely remember learning this. Yes, it has meaning. It does mean something. I just forget what it is. So with that, we coded all the students' responses. We had 30 students in our sample, all their responses about each of the 6 surface features of reaction coordinate diagrams using this deductive coding framework. And we summarized our findings in this figure. So here we have, on the bottom, you can see the 6 different surface features of reaction coordinate diagrams that we asked students to interpret. And on the side, you can see the levels of understanding. If we look at the ending and the starting point, we can see that students did pretty well when interpreting the meanings of these surface features. I will remind you that what's in purple will be considered correct. It was just incomplete answer. So if the response is in light blue and purple, that's pretty good. So that's what we see with the ending and the starting point. However, when we move on to looking at peak width, valley, and peak, we can see that there we can see now responses that are coded as no understanding, specific misconception, or partial understanding with specific misconception. About 30 to 35% of responses are coded that way. And finally, we move on to the most challenging feature of reaction coordinate diagrams here is the peak width, because pretty much almost all of our students in our study told us that peak width represents either time or speed. So for example, if a student was looking at a reaction coordinate diagram with 2 peaks, they will tell us that the peak is wider, takes longer, that reaction step takes longer than when the other reaction step where the peak is not as wide. Then we also made sure to summarize what were the misconceptions that we identified, the responses that are coded with green and red. And we created this figure that summarizes that. So when it comes to starting point, some students told us that the starting point represents activation energy. And when they asked to explain, they say something like, well, the reaction would not start unless activated. So this is the kind of logic that they're using here when telling us that the starting point represents activation energy. And some students told us that the starting point and ending point represent concentration of reactants and products. That was a little bit surprising, especially because when it comes to looking at the axis of the reaction coordinate diagrams that were in front of them, the axis do not say concentration. Then when moving on to the peak, a lot of students attributed intermediate to the peak, and some students were debating between intermediate or transition state, and they couldn't come to a final decision there. Same thing was with the valley. We had students debating, saying that the valley represents either transition state or intermediate. They're not sure. And we had also students say things like valley represents transition state. Valley represents another reagent being added, which is also incorrect. And also some students thought that the valley represents reaction slowing down. When it comes to the peak, we had students tell us that the peak width peak height, do not provide any kinetic information, or it does not represent any activation energy. And finally, the most problematic feature of reaction coordinate diagrams, the width of the peak. The 2 big misconceptions here is that the peak of width of the peak shows time or speed. And that's really problematic because most of the students in our study, we kind of started our interview with asking them a general question, asking them something like, what do these reaction coordinate diagrams represent? And a lot of students told us that activation energy was the first thing that they will tell us. As they talk about activation energy, at the same time, almost all of them tell us that the width of the peak represents time and speed. So with that, let's move on to now looking at drawings of reaction coordinate diagrams and see what the students' drawings reveal to us about their ability to make connections between reactions and reaction coordinate diagrams. So here we have 2 reactions from our study, one substitution and one elimination. And we have 2 drawings from 2 students. And again, I would like to engage the audience here. I would like you to look at these 2 drawings from Arina and Daria and think about what was similar in the way that these 2 students drew their reaction coordinate diagrams. Do you see any similarities in the logic that these students are using here? Feel free to write your thoughts in the chat. That will be really interesting. I see one response. Michael Evans says that intermediates are represented as peaks. That's correct. Both of these students show the misconception that they think that peaks represent intermediates, right? Then we have another answer saying unlabeled axis, which is also true. However, there's one more thing that I'm wondering if anyone is noticing about how students make these drawings. Okay, they're all exothermic, right? Okay, so they're only including the organic structure. Okay, so if we look carefully at students' drawings, we can see that students drew only one chemical structure at the starting point, at the peak, and at the ending point. So when I noticed this during the interviews, that was very surprising to me, and I made sure to follow up with the students and ask them, what does that mean? Do they really think that only this chemical species is represented at their starting point, or it's really the system of the reactants, system of the product, system of the intermediates? So now let's see what the students told me to that. some students in our study told us that reaction coordinate diagrams depict all the reaction species, which is great. Here we have a quote from Klava, who says, "I think reaction coordinate diagrams represent everything, because this reaction coordinate diagram represents the energy of the reaction, and all of these reaction species are in the reaction." However, 18 students in our study told us that reaction coordinate diagrams depict only the major species, and 18 students is really half of our sample. So here are example quotes that support this idea. So we have, I think it's from the point of view of only the major product. We should only think about the major aiming product. It's only the major structure we care about in organic chemistry. So when we got these results, this was really shocking to us, because these responses from half of our sample show that students actually don't have an understanding of what reaction coordinate diagrams could be. Because if you think about it, each peak in reaction coordinate diagram represents collisions between particles with sufficient amount of energy. However, in our study, students are really, they're choosing one chemical species out of each step of a reaction and assigning it to a reaction coordinate diagram. So this shows us that they're not thinking about the collisions between particles, and that also raises an issue when thinking about the fact that they're talking about activation energy when looking at reaction coordinate diagrams, but we can see that they really don't have a context for talking about activation energy. So we took this a step further, and we wanted to see, out of the students, how did they do when asked to make connections between reactions and reaction coordinate diagrams. And we see that out of these 18 students, 2 correctly matched their reactions with reaction coordinate diagrams, 9 matched correctly one of the reactions, and 7 made mistakes with both of the reactions. So this finding is also really concerning, because that tells us something about assessments that we write. We might ask students to make connections between reactions and reaction coordinate diagrams on our assessments, and they might do that correctly. However, here, when they were asked to draw reaction coordinate diagrams, we could see that they're actually not understanding what the diagrams represent. And when we think about this from the point of view of interpreting this learning theories, so we didn't look at the macroscopic domain here, but we looked at students' ability to make connections between the symbolic and submicroscopic domain. And what we can see is that when students in our study were looking at the symbolic domain representations, that did not promote them to think about the dynamic collisions between particles. And really, what we can say here is that when students are looking at static symbols printed on paper, that's what they're thinking. They're thinking about static symbols printed on paper, and we can really talk here about the notion that the particles that are dynamic in the minds of experts remain static in the minds of novices. And with that, I would like to say thank you to the organic chemistry students who participated in this study, to organic chemistry instructors that allowed us to recruit students in their classrooms, Brett and Zersky research groups for their input on making sense of this data, National Science Foundation and Volweiler Family Endowment for the financial support, and my PhD advisor, Dr. Stacy Lowry Brett, without who this work would have been impossible, who taught me so much. And one more thing I would like to say: if any questions remain unanswered today due to limited amount of time, here's my email on the slide. I'm a postdoc at UNL, as was said earlier. I'm welcoming any questions, and we'll be happy to continue the discussion. Email. Thank you.
Thank you very much, Maia. Again, another fantastic talk, summarizing a small part, I guess, of a very large amount of work and analysis you've done. So thank you very much for that. We've got a few questions. I'll just jump in quickly with one. The interview prompt, I was just thinking from a method point of view, the interview prompt you showed at the start with A, B, and C. I was just sort of wondering, if I showed that to some students, I think their first reaction might just be to sort of not say anything, be a bit overwhelmed. So I mean, can you just kind of give some insight from your own expertise as to how do you tease out answers from students?
So the way the interviews were structured, we first showed the students the reactions, and we asked students to discuss the reactions. Then we asked students to talk about the reaction coding diagram. So we didn't ask them to work through this task right away. They had a chance to look at the reactions first, then they had the chance to look at the reaction coding diagrams, and then after that they were asked to make connections. So it was, in a way, we were scaffolding this task for them. We didn't just, let them dive in. However, we could see that students were pretty comfortable sharing their ideas. If they didn't know, they will tell us they don't know. But oftentimes we were surprised by seeing that a lot of students were so confident in their understanding that they will tell us that none of the options that we provided them were correct, and they were just engaging in drawing their own reaction coding diagrams. So we didn't really have an issue with eliciting their understanding. They were pretty vocal and engaged.
One question here, which echoed something else we were talking about, was some students may have. Sorry, I've lost it. Hang on one sec. Oh yeah, some students may have been coded as partial understanding. This is from Nicole James, but might have internally a complete understanding, but didn't identify or state the correct points. And her question is, to what extent should we think of this as an incomplete understanding versus an incomplete mastery? And I think this is at the heart of what we're talking about here in terms of this think aloud protocol. How do we know that it's not that students don't understand something, it's rather that they haven't verbalized it?
Right. And that really gets back to the limitation of conducting interviews as a way to understanding. We were trying to be really careful with categorizing students' understanding to not just say these students don't understand. We were very explicit in our work that got published that the level that was incomplete understanding meant that the responses are correct essentially. They're just missing some detail, which makes it incomplete. So they might know this information, they're just not saying it aloud. So we cannot make claims about that. And also, we couldn't ask directly during interviews these very pointed questions because we didn't want to allude students to some sort of thinking. We want to really understand how they're thinking, what they're saying when they look at these representations.
Yeah. I think we found one more, which is, let's have a look. We've been talking a lot about peak width, so maybe the Savian group. I can imagine that some students did not think about the meaning of, for example, the peak width before this interview. I'm not sure I ever have really either. So maybe they just said things before they felt they have to answer the question. So in other words, they're just saying something because they know they have to say something about it. So the question is, did you observe stability of certain interpretations throughout the interview of students? In other words, did you feel that when you're talking to students, the same message is coming back again and again about a particular conception?
I would say yes. And the way we ask question about the peak width and about each feature, we ask them, does this feature represent anything? And if they said yes, then we will ask them, what does it represent? So, and then just seeing how many students were attributing time or speed to the peak width, that became this obvious trend in our data that I'm pretty certain that this is how think about this feature. And I totally agree that could come back to the fact that when instructors are teaching reaction coding, they don't tell students what not to interpret. They explain this is what you're supposed to look at, but then because they're experts and they're so comfortable with making sense of reaction coding diagrams, they forget that there's other features in this representation that chemists don't really attach meaning to. And but novice students, they do, because they don't know that that's not something that you can use productively when making sense of reaction mechanisms. So it comes back to when teaching, experts have to be explicit about the meanings of what to interpret and what to interpret, and what are the limitations and affordances of these models.
Yeah, I mean, I think that point comes up again and again in organic chemistry, doesn't it, where we only think of the main product that's formed in reactions. We tend not to tell students about all the other things that are happening. I think we could talk a long time about this, and I think there's one thing you're hinting there is the implication for teaching. So again, I'll definitely put up a list of your publications on our website where people can explore that more. But for now, Maia, I'll just say thank you again very much. And oh yes, that'll be great. That'll be there for the record. Yep, just go for it.
Yeah. I have a slide with some ideas that will be helpful for instructors. My publications discuss these things in more in depth, but for the sake of the time, I won't be talking about it. But as I said, if you have more questions,
brilliant. Yeah, thank you.
Published.
Thank you very much. Can I thank both speakers then, especially for keeping the time, because it's not easy to do a half-hour webinar on these topics, so really it's very impressive. So thank you very much for your time and sharing your expertise and fantastic work. And I think there'll be a lot of interest in following up your publications and what you've been talking about. Lots of virtual applause coming in, so thank you to the audience for joining in. Our next speaker is Rene Coe, who'll be talking next month, 27th of February. So if you're already enrolled in these webinars, I'll be invading your inbox sometime mid-February to give you details of that. But for now, thank you very much, and I wish you all the very best from Edinburgh. I'll stop recording.